All right, we're going to focus the rest of the time here in Chapter 10 looking at different types of solids, how the intermolecular forces affect what type of solid that we have. Big picture, here are our 6 type of forces again. We focus on these and we say these are intermolecular forces that occur in covalent molecules. So any two nonmetals get together, they have these, they're individual molecules and they have these intermolecular forces within them. But when it comes to solids, we say one of two things. We say that they form atomic solids when they're atoms, such as individual atoms of neon or individual atoms, if they're just phosphorus by themselves, those would be nonmetal atomic solids. Or the other term we can use is molecular solids. And it's pretty simple. They're molecules. Things like water, things like carbon dioxide, those would be molecular solids. This does not include things that are ionic or metallic. This is only for covalent substances with these intermolecular forces. When they form solids, we call them atomic or molecular. And we'll get into the differences here in a little bit between the rest of them. But there are 3 other forces, and we don't call these intermolecular because they're so large they make large, big repeating molecules. Things that are metallic, this is the first time this year we kind of talk about those. They look like they're individual atoms, but if we had iron, it's not a nonmetal, it's a metal, so it forms a metallic solid. Copper, gold, most of the periodic table is metallic. Ionic, we have metal, nonmetal, there's nothing new there. And covalent network is a new category. It looks like covalent, but it's like a repeating covalent structure. And there's only a couple examples of those that we need to really worry about. It doesn't fall into the covalent category of LDF, dipole-dipole hydrogen bonding. But those are a big picture, different types of forces and the solids that they make. So let's start going through them. First thing we need to do is just classify what do we have. What are the solids? Well, Fe is a metal, so it will form a metallic solid. Neon is a nonmetal, and it's by itself, so it will form an atomic solid. We don't really call it covalent, but it's not attached to anything, but it's by itself, it's a nonmetal. And there's a difference between those in just their classification. C2H6 is a covalent structure. It has London dispersion forces, but the solid that it forms, which is part of the question up here, the solid that it forms is a molecular solid. It's a collection of individual molecules. Calcium chloride, this is our ionic substance. Graphite, if you've seen the reading or some other things, you'll catch that this is a covalent network solid. It'll be one of our examples later. And H2O, again, hydrogen bonding, it is a covalent structure. It forms a molecular solid. Okay. In your book that we read, talking about the type of ionic crystals that can form, you can kind of glaze over those things. They're not in the curriculum anymore. There are, and you kind of stick with the examples and you'll be okay. Define molecular solid, we already did. This is a covalent structure that is a molecule. Examples would be water, carbon dioxide, any covalent structure you can think of would form a molecular solid. Generally those have weaker forces than the other things, but even things that are LDF, and this is something you kind of wrap your head around, even covalent things that have London dispersion forces can still be solids. That means that those forces are really strong. Classifying intermolecular forces is not always cut and dry. They can cross over. You can have something that has London dispersion forces that actually has stronger forces than things that have dipole-dipole forces or hydrogen bonding, just because of the nature of how big this structure is with LDF forces. So really you look at properties. Properties are going to be the giveaway here. You'll never have to predict these weird examples, but if you have a substance that is a solid at room temperature versus a substance that is a liquid, the solid substance has stronger forces. It doesn't matter if it's LDF and the other one's hydrogen bonding. The solid substance has stronger forces because it's being held together as a solid. So you can always look at these properties to tell you, to confirm strength of intermolecular forces. How would an ionic solid differ from molecular? Ionic, again, there's that word, ionic, you get a metal and a nonmetal. And this is just to reiterate that word molecular means covalent solid. So it's the makeup of the atoms that are going to be involved. So let's get in then. We're going to go metals, ionic, and covalent network here. Metals, you did some activities with metals. There are a lot of metals that you're aware of that are not on the periodic table. It's because they are alloys. Alloys are a mixture of metals, all right? It is a solid mixture. It's really weird to think about that. We're usually in the aqueous world, but solid mixtures also exist. Alloys are very, very common in our world. Brass, steel, white gold, jewelry, bronze, lots of these things are mixtures of metals. And what we need to worry about with alloys is a little bit more than a definition. We need to get two different qualities, definitions down, and classify them, and then kind of predict how two elements might react. The two different terms, here's one here, and if you remember the pictures are a good giveaway. Interstitial is the first one, an interstitial alloy. In the inter, you just kind of see the between again. So here we have the purple molecule A and then the black molecule B. And the black ones fit in between, inter the spaces. They're in between the purple ones. If those black ones were totally gone, the purple ones would be exactly where they are, now, with no differences whatsoever. The black ones just fill in the gaps that are naturally between the purple ones. Those gaps would still exist whether or not those black atoms were there. So an interstitial alloy is going to take a small atom that is able to fit between the gaps of a larger atom. And they're both metals, so we look on the periodic table and we say, okay, how would copper interact with gold? Gold is much larger than copper, so maybe it would fit into this interstitial alloy. Carbon can actually jump in here too. Carbon gets in things because it's really tiny. It can fit between the gaps and strengthen some metals as well. Steel is a good example of iron and carbon. So it fits within the gaps, and it's a size difference between those alloys. Now you can imagine if those gaps were there, and then we start filling these gaps with atoms, this is going to affect the properties. This is going to be able to bend less malleable. It's going to be more rigid, more likely to break, but it can make it stronger. It just depends on different, whatever qualities we're looking at that time. It also is going to make it more dense because it's the same amount of volume, but now we're putting more stuff in it. So we can just apply some simple definitions to see how will these properties get affected depending on what property we talk about. We just think about, okay, what is this definition, getting the atoms inside the spaces, and how will that affect whatever property they talk about. And they might throw some weird properties at you, but you just think, how is that property defined? Like density, mass, and volume. We're putting more mass in the same amount of volume, it's going to be more dense. The second one is called a substitutional alloy. Okay, a substitutional alloy. This takes two metals that are about the same size, and it just takes one out and puts the other one in. So if we wanted to take another black atom away and turn it red, we'll substitute one for the other. Now this isn't really changing the density because you're changing the same sized atoms. So take one out, put the other one in. It's not going to change the properties too much. You might change the color a little bit, but it's going to be about the same flexibility, malleability, conductivity. It has about all the same properties because they're the same size or similar sized atoms. So you can look at the periodic table and predict if you think two atoms will form a substitutional alloy or an interstitial alloy, and then define what those two things are. Why do metals conduct electricity? They conduct electricity, and then here, why are they malleable? Because of what exactly metallic bonding is. Metallic bonding if you got the definition from your other resources, has a sea of electrons. Okay, it's not a covalent bond between two atoms. All of these atoms have their outermost orbitals totally overlapping. So this orbital here is overlapping with this one, which is overlapping with this one, and this one, and this one. And the electrons can literally travel anywhere they want. They're not stuck between two orbitals anymore. This makes for some very interesting properties. If you don't have a rigid bond, then you don't have to break. You can bend. This is where malleability comes from, because we don't have a rigid bond between two things. If you hit one of them, the electrons can just go somewhere else and allow for those changes to occur. This is also why we conduct electricity, because those electrons can move all throughout the structure. And electricity is moving electrons. So this electron sea model, it's overlapping orbitals everywhere. That's what a metallic bond is. A metal-metal bond is two overlapping orbitals everywhere. The electrons can travel wherever they want. And that's what's responsible for metallic properties. And then we're going to get into some ionic properties. And this will be really, really quick because we've done this many, many times before. Identify the substance with the highest melting point. Well, they're all ionic, so we're just making comparisons within the ionic structures. And we go back into our Coulomb's law, Q1, Q2 over R, size and charge. Charge being more important than size. And we can look at these and say, okay, +1 - 1, +2 - 1, calcium chloride is +2 - 1, aluminum chloride is +3 - 1, and when we get those all multiplied together, the aluminum chloride has the largest charge differential. That will be the strongest ionic attraction, the highest melting point. The NaCl over here will be the weakest. And then we look at set number 2. They are all +1 - 1, so the charges do not matter. So we look for the smallest one, because the smallest one is inversely related because radius is in the denominator. Lithium fluoride is going to be my smallest one, so that'll be the strongest because they're going to get together. The smallest radius should have the strongest attraction because they can get closer together. And that should be a review from a lot of other things we've done. Do ionic solids conduct electricity? Why or why not? No, they do not. Because you have to have moving charges to have electricity, and ionic substances are stuck in a rigid lattice. They have charges, but the charges can't move. So we need those to be aqueous or liquid in order for those charges to flow. Ionic solids does not conduct electricity. Are ionic solids malleable? Again, no. They have a very, very rigid lattice. And if you hit this, if you tried to bend it, you're breaking. There's an attraction there, there's an attraction there, there's an attraction there. If you tried to bend it this way, you would just break those charges apart. These positives are going to repel one another. So any movement here, and you're going to get a lot of repulsions, and they just start repelling one another, and this is why they just break. They are not malleable because they have rigid positive and negative attractions. And then we get into the last part here is going to be covalent network substances, mostly looking at the carbon family for a couple examples. These are just a series of definitions. I don't think many of these will come up. Graphite and carbon, oops, that was supposed to be a pen. Graphite and diamond are going to be the types of carbon that we use the most for covalent network structures. Buckyballs and nanotubes get into our nanotechnology, which is loads of fun, but not too much of the AP course. Another category I'm going to add on here when we get to carbon is polymers. Things like rubber, cotton, really long covalent structures that they form covalent networks. That repeating carbon covalent bonds that you've seen defined as a covalent network structure. I want to look at a couple in a little bit more detail. Graphite, and then we'll get into diamond. Graphite here, these are two images of graphite. If we draw this, graphite is an sp2 hybridized carbon structure. And it kind of forms this ring. And it's this repeating ring over and over again. And you can just kind of get these carbons absolutely everywhere. Repeating structure over and over again. That's what makes a covalent network. It's not just one covalent bond, it is infinite covalent bonds repeating everywhere, all over, all over, all over. Some properties that this allows, though, if you remember when we get sp2 hybridized, there's an extra p orbital that is not being used up. That's an important property for graphite because every one of these carbons has an extra p orbital in it. Now, back in chapters 8 and 9, we talked about this being useful for delocalizing electrons, and it was a form of resonance. Well, what happens when we do this with a covalent network structure is it's not just delocalized electrons that give me a little bit of resonance between 2 or even 3 resonance structures. Those electrons can be delocalized on all the carbons. That means that all of these extra p orbitals form delocalized, if I could spell, form delocalized electrons, orbitals. They overlap and they form one orbital. If you put an electron in that orbital, he can go anywhere he wants and back again, and he can go absolutely all around in that delocalized single orbital. That is the basis for electricity. So graphite that you write with, your pencil, conducts electricity. A couple of things when we get into this, a little bit more detailed here, is this is a flat structure when we go back to the Lewis structure. You've got all of these carbons, that planar, this is trigonal planar. All of these carbons, they form a very flat surface. So what happens is you have a very flat surface of carbon, a ring, and then you have another ring on top. Your graphite pencil actually has layers to it. Within the layers, you've got covalent network structures this way. Each plane is a covalent network structure. Between the layers, however, we actually have some LDF forces. That's why you're thinking graphite, it's not the strongest force that we've studied in all of these units, but it actually is. It's a covalent network structure. It is one of the strongest forces on Earth. Your graphite pencils break so easy because you're actually breaking these forces between the planes that are actually just London dispersion forces. But if we just took a single layer of graphite, let me do this, and I'll kind of draw this diamond shapes. If we just took a single layer of graphite and we were to put an elephant on this single atom right there, on a single sheet, if we had a large enough, a long enough, one atom sheet of graphite, it's actually a molecule we call graphene, a single layer of the graphite. And if we were able to get a blanket of it, a single atom thick, the elephant could stand on it, a single atom, and not go through. It's actually one of the strongest substances in the world. Covalent network bonding. It's pretty cool. The one that we're going to look at is diamond. You see diamond, it looks the same way, except it's carbon with 1, 2, 3, it has 4 bonds. Why does this one have 5? We'll ignore that. Here's 1. All right, quick eraser. That top one looks like it has 5. I don't know what's going on there. Here's 1, 2, 3, 4. It can only have 4. 1, 2, 3, 4. It is tetrahedral. In 2 dimensions, it looks bizarre, but we can just take these carbon bonds and go infinitely in all directions everywhere. But it's a 3-dimensional structure that looks more like this. Now, there are no delocalized electrons here because this is sp3 hybridized. All the orbitals are taken up. There's no resonance, no delocalized electrons. Diamonds do not conduct electricity. They are actually amazing thermal insulators because they are not conductors. But diamond is the strongest substance on the hardness scale that we know of. These infinite covalent bonds everywhere make it extremely strong. Silicon can also do this. It's just below carbon on the periodic table. It's too large to form a silicon network by itself, like carbon does. But what it does, memorize this molecule, SiO2 is quartz. It forms a covalent network. It's too big actually to get double bonds and form like CO2. You'd expect SiO2 to do the same thing. It's too big to get those double bonds. What it does instead is it forms a covalent network. We get quartz. It's actually the same thing. Glass. It's pretty hard substance, and it is very, very, very strong. Sand. These are all kind of the same thing here. They form this covalent network with the silicon dioxide. It is a covalent network structure. Memorize this for the AP test. Covalent network solid, one of the strongest substances in nature. It's SiO2. And while we're on the topic of silicone, I'm going to post a video for you to watch for silicone to see how this relates to modern transistors and semiconductors. You need to know what N-type and n-doped and p-doped semiconductors are. Doping, much like you hear about in the Lance Armstrong world, is performance-enhancing drugs. That's actually what semiconductors do as well, and transistors and computers. We dope them with chemicals to make them perform better. And N-doping and P-doping are just chemical substitutions we make within a covalent network to make it conduct electricity. Overview here. Carbon, we just got done saying, not carbon, how is everybody? Silicon. We take silicon because silicon is a semiconductor. Silicon has 4 valence electrons. It can form these silicon bonds in 4 directions, absolutely everywhere. Okay, and it is a semiconductor already, but we can enhance it with other chemicals to make it conduct electricity even better. This is what your computer processors are made of. So we have this semiconductor that is silicon. We need it to be N-type or P-type. Well, N-type is negative. Negative means we have an extra electron. So if silicon normally has 4 electrons, valence electrons, let's pick something that normally has 5, nitrogen. If we erase one of these silicons, that's not the eraser. I don't know why I can't erase that. Okay then. If we take one of these silicons and replace it with nitrogen, nitrogen has 4 electrons too, but it also has a 5th electron. That 5th electron is now able to move around in the structure. So our N-doping is negative doping, and it has 1 more valence electron to let it move around. If we did a chemical with 1 less, we could do aluminum, which only has 3. So we just take one of these silicons, and if we made it aluminum, I'll take this one over here. We'll make this one aluminum. I don't know why it's not letting me erase. Aluminum only has 3 valence electrons, so 1, 2, 3. And it's missing a spot right here. So it creates a gap. Well, my N-type has an extra one, and my P-type, that's kind of positive, it creates this missing positive gap there. You can imagine how this negative one will find its way in the semiconductor over to this P1, and it'll allow that to fill a gap. So it controls the flow of electricity a little bit better. In terms of N-type and P-type, you just have to kind of define that I can have 1 more or 1 less electron than silicon, and identify an atom that satisfies that criteria. If you watch the video on transistors and semiconductors, you'll understand a little bit more nuanced why this is important. This is another odd topic that's been added to the AP curriculum for nefarious reasons. But we're going to keep it simple with definitions and identifying elements that meet those criteria. So the very end then, really what we're trying to do is classify all of these forces. So let's begin. SiO2 covalent network. Let's get the wrong other pen out. That is our quartz covalent network. H2S, that is covalent, bent, that has dipole-dipole forces, and it forms a molecular solid. SiH4, that has London dispersion forces, and it could form a molecular solid because it's covalent. Calcium nitrate, this is ionic. We put all 6 together now. Graphite, that is another covalent network. C4H10 has LDF forces, and it could form a molecular solid. Neon has London dispersion forces, and this would form an atomic solid. It's a nonmetal atomic solid. We always keep those solid definitions in the back of our head. Iron is metallic. It forms metallic solids, and it has a metallic structure. Apologizing for the formatting over here. We go into our next category. NaCl is ionic. Tungsten is a metal, so we say metallic. pH3, I'll skip down here, is dipole-dipole. That is a covalent structure that's trigonal pyramidal, has dipole-dipole forces. Diamond forms a covalent network. That's carbon. PCl6 is going to have London dispersion forces. Octahedral, totally nonpolar. Just kind of bouncing around here. Calcium is a metal. It is metallic. CH3, CH3, NH2. It's got this NH2 over here. This will actually form hydrogen bonds. It is a polar substance. It has that nitrogen-hydrogen bond at the end that'll form hydrogen bonds. And this is our strange one here. Okay, this is a new one, and you could kind of go 2 ways with this. Hydrocarbons, we say, are nonpolar. They have London dispersion forces. But this N in the middle kind of means infinite. You could have as many as you want there. You could just make a string of carbons infinitely long in the middle. If you wanted to have 50 of them, you could have 50. If you wanted to have 5,000, you could have 5,000. This is kind of the basis for, even though that's a hydrocarbon and it's nonpolar and it has London dispersion forces, this is kind of the backbone for polymers. And if you had like an individual chain that had a length, you could say London dispersion forces. You could also call these covalent networks. In general, they're nonpolar, but if they get long enough, they become incredibly strong substances, and they can have covalent network structures. So either way you wanted to go with that would be acceptable, depending on the context of the question. So again, you can see classifying is still the main skill that you need to apply, and you need to have the definitions down in order to do that. There's a lot of definitions in this chapter.